You are not hearing me?
I'm hearing you. Like good.
Okay. No, because okay, I, I got the message late. Okay. And if you are hearing me, that's good. So today we are going to have a set of tutorials about the Rescue Simulation League, more specifically about the Rescue Simulator. And I will be the one providing some more information or introduction about what is RoboCup Rescue Simulation League, what it does, and I will provide more details about the simulator. So the agenda for today, for those who are new to RoboCup, is to give a brief overview about what is RoboCup and what are the different sub-leagues under the RoboCup Rescue Simulation or part. A brief overview about natural disasters, but really brief. And then we are going to get into more technical details about the simulator and some other tools and the internals of the simulator and how you can implement new teams of agents, as we usually call it. Okay. The idea here is that this tutorial should be more interactive. So feel free to ask questions, interrupt me at any moment if you have questions. I also have the chat open in my window. So if you don't want to speak or you can't because you don't have a microphone, just type the question and I will try to answer as soon as possible. Okay. Before we start, I would like to know who is familiar with RoboCup simulation. If you can send a message on the chat or unmute yourself and say something. Yeah, Arno. Yeah, Arno is one of the is in the league. I think longer than I am, for sure. Is already familiar. Then we have Kevin, which is familiar. He is a coach in 2018. Nice. Okay, so sorry if I pronounce your names or last name wrong, but Eichmann is a new, and I forgot to introduce Porsche. Again, sorry if I pronounce your name wrong, but he's going to be our host for today's session, and he is the host also for the RoboCup 2022 event. And thank you for preparing and organizing this tutorial today. Okay. Okay, I'll assume that not everyone, well, except for visitors, that is more familiar. The others have a basic knowledge or no knowledge at all. So I will start from the basics, and I will go through what is RoboCup. I think in the RoboCup, presenting what is RoboCup is not a very interesting, but maybe some people are outside from RoboCup since I publicize or announce this tutorial in different mailing lists. So what RoboCup is an international effort that tries to foster the artificial intelligence and robotics to different standard problems in social relevant domains. It started in '96 and it's managed by the RoboCup Federation. As you can see, in '96, artificial intelligence and robotics was not a hot topic as it is today. So there is a long history of interest in this topic from the research community. And you can identify that by seeing the number of countries and people that get involved in the competitions that happen yearly in different parts of the world. So there is usually 3,000 participants in 40 different countries. This was before the pandemic happened. Now this year is the first year that we have an in-person event. I don't have the numbers with me, but I learned from Porsche that there was a greater number of participants, more than they were expecting, actually. Well, the RoboCup is divided in different, what we call leagues, but I prefer to call them working groups, because they are working groups dedicated to different applications of AI and robotics in different socially significant domains. There is a domain for RoboCup at work that will develop AI and robotics for helping on the industry. There is a RoboCup at home to help elderly or different kinds of activities at home. And there's also the RoboCup Rescue, which is the one that we are going to talk today. Okay, so the RoboCup Rescue Simulation Working Group, it was created after the beginning of the RoboCup. It was created in '99, and the idea is to promote research and development in the domain of natural disaster. The idea came after the huge earthquake that happened in Kobe in Japan, and the idea is to develop tools, AI and robotics tools, to support in the planning and decision making of rescue teams in a post-disaster urban setting. Okay. This working group has also 3 different leagues. There is the RoboCup Rescue robot that deals with the hardware. So they build the robot that will navigate on disaster areas in order to identify victims and notify rescue teams. There is the RoboCup Rescue Virtual Robot, which is a virtualization of the robot league, in the sense that it tries to simulate the real robots in a virtual environment in order to try to explore these virtual environments to define new strategies for planning and decision making in the disaster scenario. And there is the agent simulation, which is basically what we are going to discuss today. The agent simulation deals with the planning and decision making, the coordination of different teams of agents in order to explore and exploit different disaster scenarios. Basically, it is focused on earthquakes, but we could simulate other types of disasters if required. Okay. So the main idea, just to give an overview, why these 3 different leagues. The idea was that since the beginning, we still didn't realize it, but we work towards that goal, is to integrate these 3 leagues, in the sense that the agent simulation defines coordination strategies that is going to be assessed in this more software environment. Once the coordination is defined, they will be deployed in a virtual environment where the real robots are going to be simulated. So we will have more constraints regarding the movements of the agents in the environment, while in the agent simulation, agents move more smoothly without trying to replicate the problems of mechanics or physical problems. The virtual robot already implements that part, so it becomes more challenging. And once we solve this coordination strategies in a virtual environment, we can then deploy to a team of real robots that is going to explore and perform the activities in a real environment. So that is the main goal, to have the three leagues coordinated. One defines the coordination algorithm, the other tests it in a more realistic environment, and the other deploys it in a real natural disaster. And this is actually the goal of the league. By 2050, we should have a team of robots performing rescue in a disaster environment without the assistance of humans, completely autonomous. And well, as I said, the main goal of this tutorial today is about the rescue agent simulation. It has three goals. The first one is to develop the simulators that I will go through the details today. The second one is to use the simulator to evaluate response plans that are elaborated by policymakers, for instance. And the third one is to organize competitions and different events to promote this topic of natural disaster to the public. And that's what we are doing here today, basically. All right, so this is just to give an overview of the RoboCup. About natural disasters. Again, here I will give just an overview of what is a natural disaster and what we consider, why this is an interesting topic to do research or to work on. So, as we know, natural disasters are major adverse events that happens without much previous warning, especially the ones that we are thinking when we are talking about the rescue agent simulation, which is earthquake. There is very little pre-information that we can gather to predict when an earthquake will happen. And when it happens, it generates or causes a great impact on the infrastructure and the environment that it affects. So we see a huge loss of shelters, food shortage, or even the spread of infectious disease. So since the effective monitoring of the pre-disaster is not something that is possible, we need to deal with the after matters, which is the response, disaster response activity, in order to reduce the economic losses and the fatalities due to that disaster. Okay. Just to give some figures here, the 10 deadliest earthquakes since 1900 are listed here, ranked by the death toll. Of course, these are approximate numbers, especially the ones that are rounded, but as you can see, there has been and there are several major natural disasters happening all the time. Here are two of the main examples. One in Puerto Príncipe in Haiti that happened not so long ago, 12 years ago. And well, as I mentioned, there is a disaster management. There is a whole area of study on disaster management, and they usually split the disaster management cycle in these 4 areas. One, you can mitigate, so you kind of prepare your infrastructure to mitigate any possible disaster. Then you prepare in case of disaster happens. Once the disaster happens, which is the event, then you need to apply some responses, rescue response team to reduce the losses, as I mentioned, and later you will have a long way of reconstruction and recovery. Okay. On this cycle or simulator can be helpful in 2 parts, in the preparation and in the response. even though it's more clear that it will help in the response of an emergence, or at least in simulating the response, but it can also help in preparing the team. So the evaluation of policymaking on disaster can help policymakers to adjust their planning and prepare for in case a disaster event happens. And well, of course, the response is something that we will simulate in our simulation. Okay, so these are the two main areas that we may help. And why this is important? And usually the response phase is important because it has the objective of saving lives. So as fast and as better you do this job, more lives you save. You may prevent new disasters in some cases. You may be able to collect data for the preparation in the future, and you be also have to plan for short or long term. But when you are in a response phase, you have a lot of limitations. For instance, if an earthquake happens, most of the infrastructure of the area may have been damaged, and you will not have all the resources, especially communication resources that you have in a normal environment. So you have a limited resources, incomplete information. You will not know what is going on everywhere, so you are not able to collect the information. You need to make a very quick decision since there is a life-death situation. You will have a large number of people involved, not only the victims of a disaster, but also in the side of the response team. And finally, these teams are going to have heterogeneous knowledges and capabilities. And these are the characteristics of this environment that we try to reproduce in our simulator in order to try to run or test different strategies as close to reality as possible. Okay. Is there any question up to the moment? Up to now is just an overview about RoboCup and the. Okay. We are going to get into a little bit more technical details about the rescue agent simulator. And I have some hands-on activities that I will ask you to perform on your own, and I will be here to help. So this tutorial is supposed to be very hands-on tutorial, even though I'm going to speak quite a bit in the beginning. So the rescue agent simulator is a platform, a simulation platform that tries to represent a natural disaster scenario. As I just showed you previously, the characteristics of the scenarios are that you have limited resources, you have unreliable or limited information, you need to make decisions on the spot very quickly, and you have different types of agents to coordinate. Well, we will see it later in more detail, but the RoboCup Rescue Agent Simulation Platform is a multi-agent simulation system. So it's based on the concept of multi-agent systems, and it's composed of multiple components. So if you look at the figure on the right, the simulator are the ones in the kernel, the main object, the viewer, and the simulators. And the agents are the teams that are implemented by different people. So basically, you have the kernel that coordinates the communication among all the other components in the simulator. You have the viewer that presents in a graphical way, a visual way, and the results of the simulation. The domain object you can assume is the environment, so it's the computer representation of the elements in the environment. And you have a set of simulators that are connected to the kernel. each simulator has a one responsibility in the whole simulation scenario. The first one is the traffic. So how the agents move on the scenario is dealt by the traffic simulator. We have the collapse simulator that uses the information about the buildings in the area to determine how much, and depending on the strength of the earthquake, how much of that building will be damaged and how much of that damage will block the road in the city on the map. We have the clear simulator that it's used by one of the agents to remove or clean the blockage from the road, the ignition, and the fire in order to simulate the spread of fire in a city. And there is some other miscellaneous simulator that simulates how much civilians are damaged and how much they are buried under the debris in the collapsed building, and in which rate they may, here's not a nice thing, but in a disaster, people die. So here we simulate also the death of civilians. Over time, there is a decrease in the health of the civilians up to a point that they die. Okay, so this, we will go through more details in a bit, but this is how it looks like in the viewer, the simulation interface. This is the environment. Here's the Kobe, Japan, part of the Kobe, Japan city, with these roads represented here, and also the different buildings that we have. And these dots, colored dots, are, as we will see in the next slide, is different types of agents. We have 4 different types of agents. We have a rescue agent, which are the ones that perform activities to rescue civilians. So we have the ambulance team, which represents an ambulance, and it's responsible for unburying the civilian and transport the civilian to the hospital, which we call here a refuge or shelter. We have the fire brigade that is responsible for fighting or extinguish fire and to also unbury civilians from the debris. We have the police force, which is responsible for unblocking the road or cleaning the road so the other agents can navigate and perform their activities. And we have the civilians that starts with a green color, which means that they are very healthy, and then they will, over time, will be degrading up to the point that it becomes black, meaning that the civilians have died. And in addition to these agents that move on the environment and perform activities, we also have some center agents that we call center agents that are useful for helping coordinating the activities of the different types of agents. Then we have the ambulance center, fire station, police office, and all these centers they have no hard-coded behavior. Their behavior is defined by the teams, by us, the programmers, and the same is for the rescue agent here. And we will learn later today how we can make changes to that. But before that, let's go to overview of how the simulation plays. So we have an environment. And we have these different types of agents, that's the ones I just mentioned to you. These agents will perceive the environment. They have a range of perception of the environment, so they cannot see everything on the environment. They can see only up to a certain point, kind of replicating what we humans can observe or perceive. Once they perceive, they can update their beliefs about the environment and about the other agents that they observe in the environment, and they can make some decisions about that in order to act. Once they decide how to act, they sorry, they actually act in the environment, and this action will change the environment, which will be perceived back by the agent. In addition to the perception and action, it also have the communication capability, so they can communicate among themselves, the different rescue agents, so they can coordinate their activities in order to improve the performance of the rescue team in a disaster environment. Sorry again. The environment, as I said, tries to replicate a natural disaster environment and a real one. So it is partially observable. So not all the agents can observe the agents cannot observe everything that is happening in the whole map. They observe just a range, they have a limited range of perception. But there is one thing that they know from the beginning is this map. It's like if we are someone that is planning a response to a disaster response, we can go and get the map of the city, but looking at the map, we don't know where the disaster happened, where are roads blocked, where there are fires. So they are partially observable, the disaster. Sorry again. The environment is dynamic, so it changes the state over time. So civilians lose their health, and the fire is spread, and even the collapse can happen multiple times, even though we don't use it much frequently, but it can be set up. And it's stochastic, so it's randomly generated, so you cannot know in advance which are going to be the initial and the evolution conditions of this environment. The communication can happen in two different ways. The first one is a voice communication. So if the agents are close together in a certain limited range, then they can talk to each other. That's the meaning. Or they can subscribe to a radio channel, and they can listen to that radio channel or broadcast messages on the radio channel. The communication also tries to replicate the natural environment, so it's restricted. There is a limited bandwidth that the agents can communicate. It's configurable, and it's unreliable. You can also include the probability of messages to be dropped when sent by an agent. So all these are the richness we try to include in order to make it more realistic. Well, is there any question for the moment? Okay. I'm going to show you now the architecture. Well, I already showed you the architecture, but I will give you a more detailed explanation of how the communication happens between these different components. Okay. So the architecture of the simulator is this one. As I said, you have a kernel that connects all the other components. The domain object you can think of as an environment. The simulator represents the simulator as I discussed, and the viewer is the graphical interface that shows the results of the domain object. Okay, and the agents are the ones that listen to what is in the environment, perceives what is in the environment, and issues some commands that will be performed by the simulator. Let's go. So when we have the initialization of the simulation, the kernel gets all the information from the environment and sends them to the viewer, so they see the show. It sends it to the agent, so they know the map where they are in, and sends also the information to the simulator, so they get initialized and set up for the next steps of the simulation. Once the initialization happens, then we start what we call the simulation cycle. And the simulation cycle of this, the RoboCup rescue, it starts with the kernel sending the sense information to the agent. The idea, remember that I said that the agents have a range of perception. So the kernel observes in the environment what are the possible disaster situations or features that each one of the agents can observe. It packs it into a sense object and sends that information to each one of the agents. So the agent receives what happens in its surroundings. Once the agents receive, they can perform some activities or decide to perform some activities on the environment. If you are the ambulance, you may decide to unbury some civilians, or you may decide to go to some other place or transport someone to a refuge. So they issue commands that are actions to the kernel. The kernel then sends that information to the simulators. The simulators are the ones responsible for performing the actions, which are going to be then reflected into the environment, obviously. So the actions that are simulated by the simulator are reflected in the object representing that simulation, and the information, the kernel also notifies the viewer. Once the viewer receives the notification, it communicates with the environment in order to get the updated state of the environment and update the view. Okay. So here, up to now, we have seen an overview of how the simulation runs. Is there any question? Okay. Well, now we are going to, since now we understand a little bit better how the simulation server works. Of course, it's not too much in detail, but it's just an overview so you can understand what your agents, the agents that you will implement, need to do. We will learn how we can install and execute the simulator. So okay, so first of all, to install the simulator, you need these three softwares. You need Git, you need Java, and it must be a Java 17, okay? And you need Gradle. Once you have this software installed on your computer, you can download the server using this command line. So you can clone the server from our GitHub repository. And to compile, you just enter in the directory that it was created when you cloned and type just one command, which is /gradle w space complete field. This is what is required for you to download and install the RoboCup Rescue Simulator. Okay, it's very simple. We improved a lot from previous version, and it works in most cases. Well, we usually use Linux, so all the commands and instructions that I will provide here are for Linux users, not for Windows users. Linux or Mac works fine in the same way. So if you are Windows user, I suggest you to install the Windows Linux environment, WSL. I forgot now the actual number of the Linux environment for Windows, but it should you should be then able to run the server. Since it's Java based, it should run without much problem. But well, you have to install the server. The server is one part. Then you also have to install an agent, or you can implement the agent. The simulation server does not come with a team of agents in itself in the repository. You have a separate repository with it that we call the sample agent repository. Okay, it does require the same software as the server, and you can download it from the RCRS sample agent Java repository in our GitHub repository. And to compile, you just enter in the subdirectory and use the Gradle W space clean space build. It's ready to. It is already built once it's finished this command. Okay. I will go and then I will show you how we can download and run the simulator. So these two first steps was to download and compile the simulator and the sample agent. But how do we run the simulator and the agent? There is a script. So if you go to the RCRS server, to the server directory, and there is a script subdirectory, and in the script subdirectory there is a script called start.sh that runs the simulation. Runs the simulator platform. The command is start.sh space -m, so you can point to the map. Since you are in the script, we already have some default maps under the maps subdirectory. So you just point to, for instance, the code map, and you need also to specify the configuration file for that map or for that scenario. So under each one of these, what we call maps, we should call it scenarios. Under each one of the scenarios, we have the map, and we have also a set of files, configuration files that define the properties of that specific scenario. In this case here, we are running the code map. It will run the server. Once the server is running and connected, you will see an interface like this one, which you can switch different tabs to see the work view and other things. I will show you, I will demonstrate to you in a moment. And after that, we have the sample agent execution. So to run the sample agent, first you need to launch the server. Once the server is up and running, then you can open a new terminal and enter this command. You enter in the RCRS sample agent Java subdirectory and use the Gradle W space launch in order to launch the agent. The agent will connect to the server, and then the simulation maybe can be started. Okay. This is the view of the simulation run. I will go fast, and these are the different types of elements that we will have in the map. We have a blockade, which are represented as this black elements on the roads. We have buildings on fire, which are buildings that have different colors. Burned buildings, are the buildings that are in black. We have also buildings that have been contained fire. It wasn't on fire before, but now they have been extinguished by someone, so it was not completely burned. It is this purple color here. These are related to the building. Then we have the rescue element or entity. We have the ambulance, which are the white dots. We have the police force, which are the blue dots. And we have the fire brigades, which are the red dots. Okay. And we have the civilians, which are the green ones. For instance, this one is blocked in the road, in a blockade. And we may have some civilians here that are dead inside some building that burned. These are also burned civilians, and these are the ones moving around. In addition to the, sorry. In addition to these elements, we have the center. So we have the refuge that are represented as a house. We have the police station, which is a police hatch, an ambulance center, which is a hospital symbol, and a fire station, which is the hydrant. This is just the elements that you visualize when you run. When you run the simulation, if you observe on the top, you have a time and you have a score. And the time here is the number of cycles that that simulation will run until the end. And here is the score that you have on that simulation. It starts with the highest score and decreases according to this score calculation, according to this formula. I will not go into the details of this formula, but it's basically taking into account the health and the number of civilians and the amount, the area of the buildings that have not been burned or that you prevent. You as a rescue coordinator were able to prevent getting fire. Okay. Once you download the simulator, this is the set of directories you will have in the folder. The build is just the Java classes that are generated when you compile this simulator. The documentation are in the docs. Jars are the simulator jar files. Lib are the libraries that is used by the simulator. Log is where the logs generated by the simulator are placed. Maps hold the scenarios. We have kind of 15 standard or default scenarios. As we will see later, we can create other scenarios. Even though it's in the maps, we call it maps directory, it's the scenario. And well, if you want, it's an open source simulator. If you want to see the source code, it's available. So you go under modules and you will have access to all the source code for all these simulators and kernels. Well, now is the moment where I will ask you to actually install and execute a map on your own computer. I don't know how many of you will be able to perform this hands-on activity at this moment. Can you please send me a message on the chat? Okay, I don't get any message. Okay. These slides, I forgot to mention that these slides are already in. If you go, I will send the link. If you go to this link I just shared with you, you will find a PDF. There is the schedule, and besides the introduction to rescue simulation, there is a PDF link If you click there, you will get all these slides. There is a lot of slides. There is almost 100 slides. I think I will not be able to cover all of them because I was thinking on having you performing hands-on activity. How many of you would be able to perform it? Okay. All right. So, Ayushman, you are going to do it now. I will do it also myself. I will not install this simulator and the sample agent, but I will show how the execution of a map looks like. Okay. So I will stop here. Let me open my. So here I have two terminals. In one, I have the simulation server. If we look, all the directories I mentioned to you, I'm going to navigate to the script, and then there is several scripts that are useful when you are working on the simulator, but the most used one would be the start simulator. That you need to specify the map. Before I do that, let me show you a list of maps. So as you can see, we have different maps, but they have maps of different cities or parts of different cities like Berlin, Eindhoven, Istanbul, João Pessoa, Kobe, Montreal, New York, Paris, Sakai, San Francisco, and BC is kind of a virtual city. And we can, inside each one of them, there is two directories. One is called config and the other one is called map. In the map, we have some files that define the map. It's the graphical view or the elements of the map. And the config, as we will see later, is a configuration file that are used to define the scenario. Okay, I will not go into details now because we will see it later. But if we go to a script and go start sh -m maps code map, so we point to the map directory under the code map scenario, and -c for the configuration. So if we run this, it will open several windows. One of them, the main one, is this kernel GUI, but in addition to that, we'll also open the GUI. As you could see here, you saw several agents being connected. All the connected agents are going to be shown on the window on the right, top right. Okay, and we still have some agents to connect, which are the rescue agents. Okay, so now that we have the simulator running and waiting for start, we can start the sample agent. To start the sample agent, we can use the Gradle now, Gradle W, and then we can use launch. When we run it, you see that they start to connect, and as they connect to the different agents that are available on the simulator, the connected agents are then transferred to the panel in the view here. So before you can start the simulation, you should have nothing in this component manager, like I do have at this moment. Okay, so once everything is connected, the simulators and the agent, you can then start running this simulation by clicking on the button Run. Okay. You will see that it takes a while, and here is the simulation. This is the viewer. You have the agents moving on the scenario. You will see here, you can zoom in by scrolling with the mouse. You see that the blue is the police, it's cleaning the blockade. You will find, well, we don't have fire in the scenarios, but we have the ambulance here that are trying to rescue the civilians. Well, the tempo agent is kind of a poor implemented agent, so it is not performing very well, but they moving around and try to perform some activities. The civilians that are free, they automatically go to the refuge. The ones that are trapped, as you can see, they already start to have some gray color, and over time they are going to become black, which means that they have died. And the orange here means that the agent is rescuing and burying the civilian from the debris inside the building. Okay, this orange one means that. As you can see here, the score started with the highest amount, highest value, and it goes down. Here is the total number of cycles for this map, 270, and it says that they have one channel of communication. So the agents can exchange messages, which we don't see here, but it's just one channel. Okay. If we go back to the panel GUI, we can see the same view here, but if we want to know some properties of some of the elements, like if you want to know some properties of this building, you click on the building and they show the properties here. If you want to know about this civilian, you need to make it right, but you click on the civilian and it shows the attributes of that specific civilian, how much it is buried, how much how much is damaged, meaning the rate of death. In addition to this view, that you can also get further information about what is going on in the simulation, you can look at the line of sight. Remember that I said that the agents do not see the whole map. So here you can observe what they can actually see or perceive in the environment. Okay. The score chart shows the evolution of the score over time, and here is in a tabular form and a graphical form. Okay. All right, so any questions for the moment? Do you have any questions? Ayushman, were you able to install the simulator? Oh. Kevin is asking me to explain the line of sight. Okay. I got Ayushman. I got it. So I will wait a little bit to continue. So just going back to the line of sight. So agents, even though we humans can see the whole map and we know what is going on in each part of the map, because we have this nice view that is kind of we are kind of a god, let's say. The agents that are on the map, they have a limited range of perception. Okay, so this blue, or I will call blue, this blue line are just showing visually to you what the agent can perceive. Like, for instance, this agent is moving, but this police officer is moving around, and he can get information in this range here. Here we don't have the disaster. If we go back to, oh, we do have. So the blockade disappeared. So we don't have any blockade. So for instance, no one at this moment can see these civilians here, or because it's trapped and no other. Oh, now we have a police officer that we're able to see. It's close here, so it can perceive the information or perceive the other agents in the surroundings, and that information the simulator provides to the agent, so the agent can update the beliefs they have about the environment and improve their decision process. Does it help, Kevin? Okay, perfect. Any other question? Okay. As you see, the simulation goes on, and the agents are, now we start seeing some dead agents, like this one is dead, and there's some of the agents that are still alive. There's some ambulances trying to rescue. We still have one here that is not completely dead, and there is one here that is trapped, but it cannot leave, but it's not buried. It means it's not dying over time. Okay. And well, the movement here depends on the strategy that the team has implemented. This is a sample agent, so it's a kind of, it's not completely dummy, but it's not as smart as some of the teams that participate in our competition. As you can, yeah. Is there any other question? Okay, I will go on if you have some questions. So just to explain, if you are in the GUI, you can also stop the simulation, go step by step. If you want, you can continue running. So it's a set of tools that help you to debug or to implement test your team. Okay. All right. So let the simulation stop. Finished, sorry, and we'll continue now. Okay, so as I said, there is a set of scenarios that are predefined or default scenarios that we can use, but the RoboCup simulator comes with a scenario editor, and you can create your own scenario by creating the map, which we are not going to see today. We will use default map, but you can define the number of agents that you will have on the map, the centers, and also if the strength of the disaster that you want to simulate. And this is done into the scenario editor and also by changing configuration files. Okay. The scenario editor, it is a graphical tool that you can run, that you get in by running Gradle W space scenario editor when you are inside the RCRS-server directory. Okay, I will do demonstration in a second. Here, you can then load the map, and you can perform some tasks like remove all the elements from the map, place agents, place refuge, place sensors, and things like that. So before we go on, let me show you. So now it's not a script, it's the Gradle W scenario editor. Once you run it, it will looks like this, and you can click on load, and you can select a map. I will pick Berlin. Well, we saw already Berlin. Let's get Montreal, for instance. Map, open. So this is not actually a map. It's more than a map. The map is represented here. It's part of Montreal, but there is also agents. If we want to create a new scenario with different number of civilians, number of police officers, fire brigades, and ambulances, we can simply say remove all. It will clean the map of the scenario, and then we can place agents. Well, we can place one agent at the time. Like I want to place a fire brigade in these exactly here. I can click, or I can click on place agent, and I want to say I want to place 20 fire brigade in the road, and it randomly places in the map the fire brigade. The same thing you can do for the police. Let's say I want to put 10 police officers in the road, and I want to place another 15 ambulances on the map. As you can see, they are placed randomly. Okay. You saw that we can place the agent in the road or in buildings. Well, we can place civilians also. Let's say 100 civilians, and I want all the civilians to be inside buildings. Why civilians in buildings and the other agents outside? Because the civilians will be trapped and they will be rescued by the fire brigade and ambulance, while I want the ambulance, fire brigade, and police officers to be free to perform their tasks on the environment. Okay, so when we click here, all of the 100 civilians will be placed. We can also place the ambulance center. Sorry, the interface is a little bit tricky. I will need to move on here. We can place also a fire station. Let's say fire station here, and place a police officer. Okay, the white, blue, and yellow are that, and we can have also refuge. We can place refuges in different areas, in different parts. When you are adding refuges, you need to specify the bed capacity. So how many beds that refuge will have. So because agents will come and it's kind of simulating a hospital, number of beds in a hospital. 3, we may have here 5 beds. Well, we can place anywhere in the map the refuges, okay? Once we finish that, we can save or save as. Here I will just save as a scenario new. I don't want it to overwrite what the scenario, and that's it. So we, using the map of Montreal, we created that scenario with a different number of agents, and also with different sets of centers and refuges. That done is one part, but how do we define more specific things about the scenario, like the strength of the earth of the disaster, or the abilities or the capabilities of the agent. I will exit the scenario editor now, and let's go back to the presentation. Okay, so I showed you that the scenarios have a map folder, and they also have a config folder. In the config folder, they have a set of configuration files. There is many files and many parameters. I will go through the most important file and parameters into this presentation today. The first file is called the common.cfg. It's where you specify a seed, a random seed. So you can give different seeds if you want to simulate different disasters using the same map. You just change the seed, and the blockades will happen in different places, and the fire will emerge or be ignited in different locations. So this is to seed your random generator number that is going to be used by the simulator. You have the kernel.host, which is usually the local host, but you can run the simulator distributed also, and the port that is listened by the kernel, by the simulator server. The server now, the default port is this one, 27931. Okay. Previously was 7,000, but it started to get in conflict with some macOS application, so we decided to change it. Sorry. Well, then we have the kernel.cfg that has a parameter called kernel.timestamp 300. Well, the kernel.timestamp is the name of the parameter. 300 is the number of cycles the simulation will run. We don't have a minimum or maximum. You can put whatever number you want, but you can define how long the simulator will wait for all the agents to connect before it starts automatically. And this is defined here. So the kernel startup connect time 180,000, which means that it will wait for 5 minutes for all the agents to connect before it starts the simulation automatically. There is the ignition.cfg. You can place fire from the beginning in different places of the map using the scenario editor I showed earlier, but fire can emerge or ignite randomly during the simulation. And the ignition follows the lambda distribution, the exponential distribution, and the exponential distribution needs a lambda parameter, and the ignition random lambda is the lambda parameter that is used by the exponential distribution parameter. The perception.cfg, here is where you define the perception range, as this will make that blue line in the line of sight longer or shorter. We define it as 30,000, but 30,000 here means some 30,000 millimeters. So all the distances in the simulator are measured in millimeters. So we have 30 meters, basically, okay? And the rest fire, we can specify some parameters with regarding to the fire brigade. The fire brigade can extinguish fire, but they need to have water in their tank in order to perform that activity. And the The maximum capacity of the tank of water in a fire can be specified. Here is 7,500, and then the refill rate, when it's refilling the tank, it will be 500 per cycle. So if it was 0 to reach the maximum, it will be 15 cycles to refill the tank. And we have also the max distance. So from what distance that the fire brigade can throw water on the fire in order to extinguish it, which is 50 meters. It's further from the perception. Okay. We have also the clear configuration. This one is helps in configuring the police officer. So it defines how the repair rate, the repair distance from how far you can clean a blockade, how fast you can clean a blockade. This is the amount of blockade you remove per cycle, and the radius, how much on the radius, because you see that there is a 2D simulator, so you need to define the area in which that is covered by the clear command. And the collapse that defines the strength of the disaster and how much that will be blocked. But how do we define that? Well, first we can define that we will have roads blocked once the disaster happens or not, usually true. And we can define the strength of the disaster by defining the height of floors in each one of the buildings and the width or the wall extent or width of the wall, minimum and maximum. Okay, if you increase these numbers, the number of blockades generated by the simulator will be larger, and the same for the height. If you increase the height of the wall, of the floor, means there's more wall that crumbles and generates more blocks. Besides that, there is some communication configuration where you can define the voice range for how far you can communicate by voice, the size, how much bytes you can transmit on the message, and if there is some dropout and some noise in that channel. Okay. In addition to that, there is also the number of channels, the maximum number of channels, and the number of channels that the platoon and centers can subscribe to. Platoons here are the rescue agents. Okay. And the same thing you can define for the radio. So the radio, the bandwidth, we don't have the distance anymore. So we define the bandwidth and whether or not there is going to have failure or dropout. These are the possible configurations for the communication. Once this is finished, I was going to ask you to change this scenario in order to create a scenario with this characteristic. I don't know if Ayushman, if you were able to finish installing the server, the simulator, and the sample agent. Oh, okay. Yeah, version error probably is the Java. You need Java 17, okay? If you have Java 11, I think it will give you a problem, an error. Well, yeah, okay, yeah. Good. Well, I will, before I go on, I will give a brief overview about how to create the scenario that I posted on the on slide here. I will try to reproduce this scenario that I have on the slide. So let me launch again the scenario editor. How do we create this scenario? I'll just move to my other window. Okay, so my instruction was to copy. Let me stop again, sorry. Let me go to the maps. I will copy from Berlin to Berlin 2. Now, so this allowed me to clean up, create a new scenario, a Berlin 2. I will go back to the script. I will go back to the Word, and I will run this scenario editor. Oops. Sorry. I will show you again. I will load now my Berlin 2 map. Okay, I want to start from scratch, so I will remove all the agents. And as I said, I want 100 civilians, and I want all the civilians in the building. I want 10 fire brigades, 10 police officers, and 10 ambulances. Okay, and I also want to place one police ambulance center. Again, sorry, I will need to here. One fire station and one police officer. Okay. So we have all the sensors, and I want also some refuges. I will place one refuge here with a capacity for 2 beds. Oh, I said I wanted 3 beds, so let me change it to 3. I want 4 refuge, so another refuge here with 3 other beds, another one here with 3 beds, and one maybe here with 3 beds. Okay, so now we created, I will save this scenario, and I will close the scenario editor. We don't need it anymore. But I also in the slide asked to change the number of cycles from 250 to 200. So this is done on the configuration. So let's go to maps, Berlin 2, and config. We have different files. I'm in Linux here, so I will use VI. VI, well, if you remember from the slide, change the number of cycles. We need to use we change it in the kernel CFG. As you will see, there is many more parameters, but well, we are restricted to the kernel time step. So I will replace 250 by 200. That's what I want to change here. And I also want to change that, make that there is no communication in this scenario, no communication. So comms Dutch. Well, there are some default configurations. In this configuration file, if you use the hashtag, it means that it's a comment. So initially it was a full communication, and now we have we want no communication at all. So we can uncomment the communication line 6. Okay. If we go to the directory comms and we add it here, you will see that this has just one voice channel, but it does not have any communication channel. It does have a radio channel, sorry. It does have a voice channel, but no radio channel allowed. So they can communicate if they are close together, but the agents cannot communicate through any other means. Okay. Once we make these changes, we can go back to the script and we can start it. Now to start, we call it Berlin 2. So oops, I forgot here the minus M and minus C for the configuration. Once we run, 1 second, it's opening the GUI here. This is what we see as a result. This is the scenario that we have created, okay? And if we connect after finishing connecting, we can then start simulation. You see that there is no communication and there is 200 time steps. All right. Is there any question? How to create a scenario? How to use that scenario to run the simulation? So I'll stop here the simulation. Good, okay. And Yushman, were you able to fix your problem, your error version? Okay, great, good. So later on, you can try these hands-on activities, and if any of you have any questions, you can contact me. I didn't send my email, but I will send the. Oh, a better approach that I will propose is that so if you go to the rescue simulation page, we have a mailing list. So if you subscribe to the mailing list and if you send messages to the mailing list, then the community can help you better. It's better than giving my personal email because it may take longer to reply, and sending messages to the mailing list is better because we share the questions, we share the answers to all the community. I forgot to mention there is some documentation also about the simulator that are available on the webpage, on the rescue simulation webpage. Everything I mentioned today basically is mentioned here also. The next part of the slides are not detailed in the documentation, so it's good that we are going to have these slides up. All right. Do you have any questions? I think Kevin said it's all okay. Ishman is fine. So let's continue with the slides then. We still have half an hour to go. I think I will be able to cover the structure of the simulation partially, not in full, but you have the slides to continue. So up to now, we saw how the dynamics happen and how to actually run the simulation and how to create new scenarios. But under the hood, meaning how is things implemented in development terms, okay? The simulator is a Java-based simulator, and it is an object-oriented, it follows an object-oriented paradigm, okay? Even though it has this concept of multi-agent systems, the implementation of the multi-agent systems is using object orientation. And here, what I will cover is the class hierarchy of the simulator and the different objects that exist that when you are implementing agents, you need to know in order to deal with the environment or deal with the actions in the environment. So the class hierarchy, I will not go into these details, but we have abstract classes and concrete classes. Like all the rescue agents are concrete classes, so you can actually instantiate civilian, ambulance team, fire brigade, and police officer. But they extend the human, which extends from standard entity, which is an abstract entity, which is an entity. In the end, the civilian ambulance team are entities in the map, in our scenario. Okay. We have blockades. The blockades are also objects in our simulator. And of course, we have the roads and the buildings that are also objects. But they are not human, of course. They extend an area, and the area have different properties. And the area is also an entity. So in the end, all the concrete classes that we have on the simulator are an entity in the simulator. Okay. Well, in addition to extending the human abstract class, the sample agents also extends the standard agent. The standard agent will provide different features to the agent. Actually, it will provide minimum structure that the agent must have in order to participate in the simulation. And the standard agent is connected to the standard world model, which is the world model or the environment model that is represented in that specific scenario. So it's through the standard agent that different types of agents are able to know what the world is and how to deal with it. So getting to a little bit more detail, well, we have the object world in the simulator, and the world represents the simulation environment. It includes, it's composed of a set of entities like buildings, roads, and humans. Everything is included in the world, and it's usually an instance of the standard world model. And all the roads and buildings inside a world are represented as a connected graph, similar to this one. So if you have these elements in the map, like the buildings and the agents, I'm sorry, the roads that are in the map, they are all connected one to the other. How they are connected? Through an attribute called neighborhood. So an agent has a neighborhood uh, property that has the link to the other roads or building blocks that you have in that is a neighbor. The standard word model, the instance that represents the world, it does have some useful methods. One of them is the get distance. So if you want to know the distance between two buildings or from your location to somewhere else in the environment, you can use, the get distance method from the standard word model, and it will give you the Euclidean distance. In addition to the distance, the word also provides the agent with the get entities of type. It provides all the entities of specific type to to who is calling this method. Okay. It also provides a list of objects or entities that are in a specified range. You can specify the range in distance, in distance, and it will return all the objects that or all the agents that in that range. Or you can specify also, so the range will give you a circle, and you can also specify the object or a rectangle by giving the XY initial position, XY final position. Well, this is the world, and this is how, so if we go back to the hierarchy, each one of the rescue types of rescue agents will have access to the standard world by default, since they extend the standard agent. So they will be able to call these different methods very easy, in a natural way. Okay? Well, in addition to the world, we also have objects that represent building, which is the build object. Okay, it extends area, as I showed, and the building has this different set of properties. It has an ID, it has a brokenness, which indicates how much damage it has been inflicted. If it's on fire, there's a fire intensity or a temperature, because it may not be on fire yet, but the temperature may be increasing, so you can test that. And also has a property for the total area of the building, including all the floors of that specific building. And okay, the blockades, a list of blockades that are in the building area. If the building collapses, it generates some blockades internally. Well, together with the building object, you have a set of useful methods like get neighbors. It will return a list of neighboring entities. I told you that roads and buildings, they are in a connected graph, so they are connected to their neighbors. And by using get neighbors, you know the entities that are neighbor of this building. Get brokenness, get the damage suffered by the building, and get pureness, it will return a number from 0 to 8, which have these meanings that are in the slide. So 0 means that it was unburnt, and 8 means that it's burnt out. These numbers are represented with different colors in the viewer, and the agent can get that information programmatically. You will also be able to get the temperature, get the total area of the building, or even understand which type of materials that constitute mostly that building. Like if the building was built in wood, steel, or concrete, and they also have a transmission rate. So when a building is on fire, it may irradiate its temperature and transmit heat to the exterior, to the other buildings, so the other buildings also get on fire. And this is the transmission rate. And also, you can get a list of blockades that are in the area of the building. In addition to the road, to the building, we have the road. A road has a unique identifier, but as a property, it just has a blockade. So on top of a road, there only be possible to have a blockade. In a building has more properties like floors, total area, and other things. Here in the road, is just a list like that. Sorry. So programmatically, you can get the blockades that are on that specific part of the road, or you can get all the neighboring entities to that road element. As I said earlier, a blockade is also an object in the simulator, and it has a position, which is an entity where the blockade is located. So it's a pointer to the entity where the blockade is located, and there is a repair cost. How hard would be to clean up the blockade? Remember the clear repair rate? The clear repair rate is a number that when the police officer apply an action of remove blockade, reduces the repair cost of a blockade up to a point that it becomes zero and there is no more blockade. Okay. So a blockade, you can get a position, which is the entity where it is located, and you can also obtain the repair cost. So these are the objects. So these are the objects that compose my environment. They are inanimate objects. But we have the other objects, which are entities, which are, sorry, they are not objects, they are entities, and they are agents. And these agents have behavior. The agents that we have, as I went through already, are the platoon agents, ambulance team, fire brigade, and police force, and the center, ambulance center, fire station, and police office. And we have just the civilians as an additional one. Here I want to show you how we can create or program an agent. So all these different types of agents that I'm showing here, we can create, program in the platform. In order to do that, we need to create this minimum class where we need to have a class name and extend the standard agent, and we need to specify the standard agent entity here. In addition to that, there's three must existing methods. The first one is get requested entity. The second one is post connect. We will see it in the next slide. And the third one is the sync. So this is the minimum structure for an agent to be able to connect to the simulator and perform action. The standard entity URL are an enumeration, and these are the possible options. The standard entity is the same. Let's go to the different methods, what they mean, and what you should do in them. So the first one is the get requested entity URN and no. You should return in that one the agent type implemented. Like if you are implemented a police force, you should return the standard entity URN dot police force. Why you need to say which type of agent you are implemented it in that class? Because when the simulator is connecting an agent to the representation in the simulation kernel, it needs to know the type, right? So the second method is the post connect, is a method to execute it once the agent connects to the simulation. If you remember in the beginning, I said that the kernel, the domain object sends some information to the kernel in the initialization, and the kernel sends that information to the agent. It's the information about the map. So the post connect is a method that can pre-process some information about the map in order to reduce the processing time during the simulation run. This post connect method may have a time limit. As I showed in configuration file, it's 180,000 milliseconds, which represents 5 minutes. So the agents have 5 minutes to perform any pre-computation they want before the kernel stops, does not allow anymore that, and it starts the simulation. And the last method, which is the most important one, is the method called think. And the think is the method that implements the agent behavior. Why is that? Because at each simulation cycle, the think method is called by the kernel. So the think method is called every cycle, and it does have a limited time of 30 seconds. Oh, sorry, it's not 30 seconds. Here is a half a second. It has between half and 1 second to reply back the command to the simulator. So it has between half and 1 second to reason about what is going on in the environment and reply some action to be performed in the environment. It does receive the time is the cycle it is in. The change set is all the elements or entities that is in its perception, range of perception that the simulation sends to the agent. And the heard is a set of commands or communication messages that it heard from the environment. So all the messages on other agents sent to these agents are received here. Is this part okay? Is it? Well, we don't have much more time, and here it's more about programming. I think you would need to go through the code, but I will try to go quickly through the next slides, and then I will show the code, just give a brief idea of how it works in reality. Okay. Well, if you want to read some of the keys that are in the configuration file, you have this .config.getInt value method that you can read from the configuration file some information, some parameter values. Like here, we are reading the perception, line of sight, max distance, and also the fire extinguish max distance. Again, this is the minimum for an example of a minimum agent of ambulance type. So here is an example. AT is a standard agent, is of ambulance type. And we are returning an enumerator and saying that the agent is an ambulance team. And in the post connect, we just capture the line of sight, the max distance of the line of sight. And then in the think, we will implement the behavior of the agent. I will go very quickly here. So the standard agents have also some properties. The agents have a XY, the actual coordinates in the map, how much they are buried, meaning that if there is debris on top, they will be stuck inside a building. The HP index, how much health index they have, and how fast they are dying. And the position means on top of which other entity they are, if they are in a road or if they are in a building. Okay, you can get all this information using the different get methods, and each one of the agents has different capabilities. The ambulance team can sense, hear, say, move, communicate via radio, rescue, load, and unload civilians. Fire brigade can do, in addition to sense, hear, say, move, it can also rescue and extinguish fire. And the police force can only clean as a special operation. So you can think of the ambulance can rescue civilians, unbury civilians, and transport them to refuge. Fire brigade can extinguish fire, but they can also unbury civilians from the debris. And the police force can clean the roads. That's basically what this capability means. I will not go into the details here. I think you can look at the slides later. What I would like to do is I would like to switch to my interface. This is my programming interface. Here is my ADF sample agent Java code. And if you download, you will be able to see this different, oh, this is the ADF, sorry. We should be looking at the sample in the RCRS sample agent Java. And we can go, for instance, to the police force. Police force is responsible for cleaning the road. So it extends the abstract sample agent. It defines that as a police officer, police force entity, and it does have a, where is the method? I think it's in the, oh, it does have a get request entity URN and enumerator to say that it is a police force, okay? And it does have a post connect method that basically indexes all the roads. So it isn't, the model here points to the word model, okay? And the index class says that this agent will be interested in roads because the police officer is responsible for unblocking roads, so it does not need to know about buildings. So it just needs to know about roads. And it also have a distance, maximum distance that it can clean something. So it needs to be closer to this distance in order to be able to issue a command. So in the post connect, it indexes the road and defines the maximum distance it can be. The further away from the blockade it should be before it issues a clean command. But the most important part is implemented here in this think method. And here, first, it checks whether it is in the beginning of the simulation, so it subscribes to one of the channels of communication channels. After that, it reads all the messages and logs it if we are running in debug mode. So it does not use the heard messages, but it does some logging. But the most important part comes in the think comes now. So the first one is, okay, get target blockade is a method that will look in my area. So location returns where I am now. It's an area. And I can look in that area to see all my neighbors of that specific area. And I can see whether or not there is any blockade in a certain distance from myself. If there is a blockade, then I will return the blockade. Otherwise, I return you. Okay, so that's it. But this get target blockade. So it tries to get one target. If the target is not new, meaning that I have a target to clean, a blockade to clean, I will inform others that I'm cleaning that target. Okay, and then I do some calculations in order to see if I'm close to that specific blockade, and I will send a clear message to clean the blockade. The command, you can look at the slides later, but each one of the actions or capabilities are implemented as methods in the standard agent. So the police can send a clear action to the simulator, informing the time, that's the time cycle, simulation cycle, and saying what are the coordinates it wants to clean. And then the simulator will actually clean the blockage and will reproduce that on the visualization, the view. Okay. Well, this is if there is a target, but maybe there is no target. The police officer could not find any blockage, or there is no more blockade in the map. Then the agent will try to do something in addition. So if it's not close to the blockade, we'll go to the blockade. This is to go to the blockade, this part of the code. And once, if there is no blockade at all, then it will move randomly in the map. So it's just random walk on the map, trying to find something to do. Okay, so you can split the think method in three parts. The first one is, okay, I have a block close to myself, and I'm gonna clean it. The second part, oh, there is a blockage, but it's far away, so I need to go first, get close to the blockage before I can clean the blockage. And finally, if I don't know and I don't have any blockade in my belief base, I just move around without doing anything. All right. Yeah, I went quicker now, and well, this part is a little bit more tricky since it's programming. But what I would suggest you guys to do is to try to follow the slide presentation and try to understand the sample code to see if you have any questions and see if you can make any changes, creating your own team of agents. As I said, a team of agents is composed of fire brigade, police force, and ambulance team, and different types of centers. The ambulance center, police office, or the fire station. You should have all of them implemented for successfully running in your team of agents in a simulation. Sorry again. Is there any specific question to what I just showed you? I suppose that this last part was very unclear, but I hope that by clarifying how the simulator works, will help you to implement your own code. Does anyone have any question, any comment? All right. If we don't have any comments or questions, we'll thank you very much for participating in this tutorial. I shared the PDF on the tutorial in the introduction in the tutorial webpage. I would like to also highlight that we have a video presentation of our invited talk or keynote speaker, Nobuhiro Ito, who is a